Okay, now, this chapter dealing with forces is probably one of the most diverse chapters because there's all kinds of different ways to look at how force is used in everyday life as well as all aspects of physics. Force is extremely important because it causes motion to stop, and all the ramifications that involve both of those scenarios. So an inclined plane, and to refresh your memory, an inclined plane is simply a triangular looking figure like so, in which you have a right angle here, and what's going to happen with this inclined plane is that we're going to put some kind of object, like a crate or a box or whatever you want to call it, and it's going to have a tendency to slide down here. Okay, that is known as Fp. So the force that is parallel to the surface is going to slide down. But what's also happening to this object, and I'll put this right here as the crate or box that we're dealing with, is that it's being pulled towards the center of the Earth. That is the weight in which it is being pulled in that direction. But at the same time, it's also making contact with the surface right here, so you got that, and that force there is perpendicular. So it goes all the way down here, say somewhere around there. And this is known as Fm, the normal force. Normal meaning perpendicular. Now, if I complete this triangle right here, you see that this resultant force right here is the same as the Fp over here. It's parallel. That's why we call it parallel force. But this angle, whatever this angle is, and we'll use the mathematical term theta, shows us that we have similar triangles here. That this right triangle that I have created right here is similar to this triangle we have right here, and therefore all the sides are proportional to each other. So this Fp and this Fp have a certain proportionality to it. Fw, which is equivalent to this Fw right here. So if I take this and flip it over this way, this is what we're going to end up getting. So we got the similar triangle here. So what we're going to do is that we're going to deal with that similar triangle and figure out the various aspects of the forces going on here. Now, when we take another look at this, we know that this is going to slide down, but is it going to slide down at the rate of gravity? No. Gravity is going in this direction right here. This is taking a side torque. And so the rate of acceleration of going down here is not going to be 9.8. It's going to be something less because it's not going straight down. And we can calculate that by using this triangle, this right triangle. And now we can see here that we have Fw, which is the hypotenuse of this right triangle right here. And then Fm is this right here, and Fp is this right here. Now, this, I'm talking in relation to this theta we have here. We have here a SOHCAHTOA situation, Caroline. And so we can find Fn because of the fact that it is the adjacent side to this right triangle with this hypotenuse, and adjacent over hypotenuse we know is the cosine of theta. And so the cosine of theta is going to be equal to the adjacent Fn over the hypotenuse Fw. And then we can use our algebraic skills to get Fn by itself, because we're going to very easily find the weight simply by taking m times g. And so multiply this by Fw, and this means that Fn, I'll use lowercase n, because that's what I did in my script. strict is going to be equal to FW times the cosine of theta. The same thing with the FP. The FP is the opposite. So that's going to give us the sine of theta over the hypotenuse. The opposite over the hypotenuse, so and now this is going to be FP over FW. So again, we multiply by FW, and FP then equals FW times the sine of theta. And those are the values that we're going to be working with in these problems. So this is the general idea. Now, this is a frictionless situation. At this point, we're dealing with the absolute theoretical stuff, meaning we know this will never really happen in real life, but the cool thing about physics is that we can pretend that we can have frictionless situations, so we get the basic idea of the theory behind it, and then when we get to friction very soon, you'll see that that has to be brought into the mix. But once we understand this, the friction part of it becomes a lot easier to understand. So, let's take a look at an example involving this. You got a 30 kilogram crate released at the top of the inclined plane, and we want to know the weight, the normal force, the parallel force, and the acceleration that travels down the inclined plane if it is a 20-degree slope. So let's draw ourselves another inclined plane. Now we have to okay, so I'm going to put my box somewhere towards the top. You know this is 30 kilograms. And this is a 20-degree angle right here. I hope it's right here. Yeah, make sure that's right. But yeah, 30 kilograms. Okay, good. So, now we're going to draw our vectors of force that is going to be similar to this triangle that we have right here. So the weight is being pulled straight down. So that is our FW. And FW can be calculated as M times G. So that's 30.0 kilograms times 9.80 meters per second squared. And I believe that comes out to be 294 newtons. Okay, so this is 294 newtons right here. Then we have the normal force right here. Okay, so that's Fn right here. And this is Fp right here. And it's P because it's parallel to this, even though my drawing kind of stinks. But this is Fp right here. And this is the angle right here. That's the same as this. So that's my 20-degree angle. So Fn, as we said, I'll use the lowercase here, so I don't want to be confused with newtons. Like it ought to have a lowercase n here. The Fn is the normal force, and that normal force, as we said, is the Fw times the cosine of 20 degrees. So Fw, we said is 294 newtons times the cosine of 20 degrees. And we said that was Fn, it says 276 newtons. When the smoke clears and our calculator smoke has gone away, we get 276 newtons. Fp then is equal to Fw times the sine of 20 degrees. So Fw then is, again, 294 newtons times the sine of 20 degrees, whatever that is, and I don't really care, because I just type in my calculator, it comes out nice and clean and round off 3 sig figs and all that good stuff. So we go over here and we see that value is 101 newtons. And it's FP here that is going to determine how fast it goes down that slope, because this slope is parallel to this vector right here, for force, this force vector. So, we go to Newton's second law of motion, which states that the force is calculated by mass times acceleration. So I'll put FP here to emphasize that. Is equal to mass times acceleration, and it's that we're trying to find out. How fast is it going to accelerate? If there is no friction, it's going to go faster and faster and faster down. Just like a skier on a hill, which has very little friction because the skis are all waxed up in snow. It's snow, and when you go down in snow or you ice skate, as you're going, the skis or the blades of the skate are cutting into the snow slash ice, causing the snow slash ice to melt, and now you have water between the ski or the skate and the surface, which is virtually zero friction. And that's why it's so important to see skiers shush around, doing this and then doing this, trying to control the fact that if they go straight down a hill, particularly a diamond or a double diamond, that's not good unless you're a professional skier. So that's the theory behind this. So it can be a lot like skiing or ice skating, but most of the scenarios will have some friction loss. We're going to pretend like there's no friction, so this is what's going to happen as it goes down the inclined plane. So this is our force right here, 101 newtons, equals the mass of the crate, which is 30 kilograms, times A. So we divide by 30 kilograms. And that leaves us A by itself, and we divide that out, go to our script, and we see that it is 3.37 meters per second squared. Okay, so now that's the whole process for inclined planes. So we have 4 practice problems for that. We're staying away from the physics books because I don't really like their problems for this section. In fact, for a lot of sections in force, they kind of get a little carried away. So a lot of the problems I'm going to be doing is going to be involving my own problems. And then we'll go back and forth between the book and my own problems. Depends on my mood as to what I think your problems are like. So these are your 4 problems there. So go ahead and get working on it, and good luck.